Yeah, originally I was gonna, of course, talk about something I've been working on, or, problems I think about. But then when I saw the title of this workshop, and especially that I was on, computational day, it's like, oh, there is this other project that I did that would be such a good fit, except that it's just really not my area. But, it's Frank's birthday, and it's closer to his area, so, it felt like the polite thing to do. So I am going to talk about a problem that I worked on with Paul Breiting, Gabriel Ong, and Linus Sommer. When I first got to MPI as a postdoc, it was an REU, and so Gabriel and Linus were undergraduates at the time. And I want you to think of this talk as like a very big, a glorified open problem presentation. So I didn't submit a problem to you, Taylor, because I'm just going to use my time slot to present. And the other good news is it probably won't take me all 40 minutes or whatever to get through this. And so I figured there'd be extra time at the end that you all can, there's like 40 of you. You can take the extra 10 minutes times 40, that's 400 minutes. You could probably solve this problem before the coffee break. Okay, so this problem is a variant of a very classical problem. So there's this problem called Steiner's conic problem. And what it asked was how many conics are tangent to 5 generic conics in the plane. Okay, so I just kind of put, randomly think 5 conics in the plane, and I can ask how many conics are tangent to these. So originally, Steiner conjectured that the answer was 6 to the 5. And you can phrase this problem actually as a system of polynomial equations, and the 6 to the 5 would actually be the Bezout bound of that system of equations. Now, the issue is that this isn't a generic system of polynomial equations, right? It's very structured, and so this is an overcount. So the true answer is 3,264. And part of the reason of this overcount is there's, in the space of all conics, there's a surface that consists of these double lines, right? And so really you don't want to consider this problem in the space of all conics. You want to consider it in what's called the space of complete conics. It doesn't matter, but we don't want to have these double lines, and so this is part of the reason that there was this overcount. I just want to say there's a couple very nice references on this kind of classical version of the problem and how you can count out this 3264, and so here's 2, but kind of largely speaking, the complex version of this problem has had an answer for over 100 years now. Okay, over 160 years, yes. So fine, but there's actually maybe a more interesting variant of this problem, which is the real version. So what the real version would say is, suppose I give you 5 real conics, so just 5 conics in the plane. What is the maximum number of real conics tangent to C1 through C5? Of course, 3,264 is going to be an upper bound, right? Because that's the complex bound. But it's not clear that this is achievable, right? That there exists a configuration of 5 conics such that all 3,264 tangent conics are real.
Holton asked that question in his thin book on intersection theory.
Okay, yes, so perfect. Thank you, Frank. See, this is great. This was the one I was like, oh, I'm nervous about talking about this because I don't really know the area that well, but I'm like, well, Frank will know the answer to every question, so I'm actually in the clear here. But okay, the answer is that there does exist, that this does exist. And so there's this theorem, and it's, what they do, the argument is that they argue that if I degenerate my conics, my 5 conics, into double lines, that in a neighborhood of this non-generic kind of special degenerated configuration, there exists 3,264 real conics. And you can count this by doing kind of classical geometry and counting conics tangent to lines that pass through points. And so Frank has a nice whole web page, as well as a chapter in his book that goes through this. And then Berend has a really nice paper with Paul Breiting and Sasha Tim, where they go through this as well and kind of consider a more constructive version of the question, namely, can I give you an explicit configuration of 5 conics that achieves this bound? Okay, so this is kind of the context for the problem we consider. And we want to consider a variant of this. So instead of considering conics tangent to conics, we want to consider circles tangent to conics. And again, we want to consider both versions. So now, a circle is defined by its center and its radius. So there's no circles tangent to 5 generic conics. So the right number of conics to consider now is 3. And so we want to ask both versions of Steiner's problem for circles. So I want to say, suppose I give you 3 general conics in C2. How many circles are tangent to all 3 conics? And then we want to also consider the real version. So suppose I give you 3 general real conics. How many real circles are tangent to all 3 conics? And kind of more importantly, what's the maximum number of real circles that I could find? Okay, so this is good. Okay, so I want to go through with both of these questions. And so kind of as before, it makes sense usually, real geometry is harder than complex a lot of times. And so it makes sense to start with the complex version. So let's kind of write this out. And so the first thing is I'm going to define my conics just in, okay, it makes more sense actually to define this in projective 5 space, but just kind of for ease of everything, I'm going to just kind of define everything affinely. And so I'm going to suppose that you give me 6 complex parameters, and those are going to define my conic. And then the conic is the set of xy that's a 0 of this polynomial equation. In addition, a circle is going to be defined by its center and radius, and it also is the set of points that satisfy this equation. And so I'm going to consider 3 polynomials of the form Q. So I'm going to assume that A through F are given, and then I want to find equations of this form, of the circle form, that are tangent to the conics. Now, a circle and a conic, of course, will generically intersect 4 times in the complex plane. And what a tangent intersection means is that it has multiplicity too. And so this can also be phrased as a polynomial condition, namely that the gradients of each are linearly dependent. Okay, so putting this together, I'm going to assume I fix my 3 conics in the plane, and I'm also going to introduce new variables, which will be my points of tangency on these conics. So the conditions of a circle being tangent to the conic need to satisfy the following 3 constraints. So first, of course, these points of tangency need to be on the conic for each conic. In addition, the points of tangency need to be on the circle for each circle. And then finally, we need to have this multiplicity 2 intersection, which are these determinantal constraints. And so kind of putting everything all together, what I'm really interested in studying is the following parameterized polynomial system, which consists of 9 equations and 9 unknowns. So my unknowns are the u's and v's and the s, t, and r, so the points of tangency and the center and radius of the circle. And my parameters are the a's, b's, and c's, i.e. the coefficients defining each of the conics. Okay, good. So this is our setup. And now let's go back to our first problem. So suppose I give you 3 general conics in the complex plane. How many circles are tangent to all 3 conics? Well, one thing is we can just look at this polynomial system. See, I've got 9 equations of degree 2. And so I can use Bezout's bound and say that there's at most 512 complex circles tangent. Okay. But this actually is an overcount because, again, we have this issue with these double lines, right? That's going to throw this off. And so in some work of Emmerich and Salmus, they show that actually there's at most 184 such circles. Now, they show this, they specifically consider the cases of where all of your conics are ellipses, but the set of ellipses is open in the space of all conics, so this still applies to us as well. And they show this using kind of a mixed volume computation and a resultant computation. And when I was looking at their paper going through it, they also cited just the upper bound is 184 citation, and I looked and it just said personal communication with Frank Sotile around 2005. And so that's that's great. Yes. Yes, exactly. And so, okay, so the answer is at most 184, and the first thing is, well, okay, generically it's 184, right? This isn't so.
It's actually, when I said the most 184, actually, it is 184.
Right, they didn't phrase it like that.
Well,
yes.
I
Well,
mean,
yeah.
I mean, you look at conics that go to 2 points and
Exactly, yes.
And circles are just 2 special points.
Exactly. And so we actually wrote it up though. So okay, and then, but yeah, okay. So that's the answer to the complex solution. But like Frank said, not a terribly challenging argument. Really analogous to the Steiner's problem argument as well. So, okay, 184 complex circles, tangent to 3 conics. Great. But of course, you know, from the get-go, we were really just interested in the real version of this question. And so, again, this question is now, suppose I give you 3 general real conics, how many real circles are tangent to all 3 of them? And specifically, what is the maximum number of real circles I can have? So kind of for any configuration of 3 real conics, what's the maximum number of circles that can be tangent to all 3? Well, I'm talking generically. I don't want, you know, don't do something where there's like infinitely many solutions or anything like this. Okay, so of course, we have one upper bound, which is 184, right? So there's at most 184 real circles because there's at most 184 complex ones. But the question is that exact? And that's really what this open problem is this exact? And we were specifically interested in finding conics with the maximum number of real tangent circles, so kind of explicit instances if we can. Okay, and so we tried 3 things, and I will walk you through each of the ideas that we tried so that when you solve this problem, you know not to, you know what's already been attempted. And so the first idea, the most natural one, of course, is to apply that same degeneration argument as in Steiner's problem. So now in this case, instead of degenerating to 5 double lines, I have 3 conics, so I'm going to degenerate to 3 double lines, so i.e. a triangle. And what I want to do is I want to use the same kind of counting argument to say, okay, in a neighborhood of this degeneration, what's the maximum number of real circles I can have? And unfortunately, the answer is not 184. The answer is 136. And I can walk you through at a high-level overview why that is. But at this point, the main takeaway is we can't just do what's already been done, unfortunately. Okay, so why does this fail? Right? Well, it fails because of some kind of classical geometry reason. So the proof idea here is, as I said, I'm going to take my 3 conics, I'm going to generate it to 3 double lines, so I have a triangle. And what I'm going to do is I'm going to consider each of my 3 lines, and then I'm going to consider a point in the interior of each of the lines. And then what I do is I can consider every subset of lines and points. And so maybe I can just draw this so it's a little more clear. So I've got here my double conic. So let's say this is line 1. And then on line 1, I've got point 1. This is line 2. On line 2, I've got point 2. And then this is line 3. And on line 3, I have point 3 at the origin. And then what I want to do is in my set of 3 lines, I want to consider every possible subset of lines, and then union with the points not on that line. So for instance, one subset I would consider, say, lines 1 and line 2, and then point 3. Yeah? No, on the boundary. So on the boundary of the triangle. So this is on the lines. These are points exactly on the lines. Okay. Okay. And then okay, you can, in this case, you can actually just verify this directly, but apparently all of my co-authors actually knew that this was a classical geometry result. They're like, oh yeah, we learned this in high school. And okay, I don't think I did, but it's not so hard to verify directly that there's 2 to this number of complex circles tangent to the given lines in S that pass through the points on the line not in S. Okay, so what does that do? Well, of course, then we have to use the binomial coefficients because I have to consider every choice, right, of 1 line, 2 lines, 3 lines, 0 lines. And I get this many complex circles that are tangents to my conics here. And then what I do is I would want to do at least is say, okay, if all 23 are real, then what I can do is I can replace these double conics by a hyperbola that's kind of asymptotically close to these double lines. So just think like really skinny hyperbolas. And then for each pair, PI, LI, I would get 2 additional circles. And so in total, that would give me 2 to the 3 times 23, which is 184 real circles. Okay. this is what we wanted to do, and this was essentially what was done in Steiner's problem, but you have to consider the other cases because it's a pentagon. So it's just, so this counting bit is different. Yeah. No, so I'm considering points on the interior, like on the triangle. Yeah. Okay, and so what I need to do is I need to figure out, so this is the complex number, right? And I need to figure out if this is in fact the real number. And the answer is it's not in one of the cases. So I don't even know if you can see these pictures, but okay, you know, the main takeaway here is if I want to say how many circles go through 3 points, the answer is 1. And so here would be my 3 red points, and this is my circle. Okay, how many circles go through 2 points in a line? There's 2 real ones, or 2 complex ones that can be achieved with real ones, as seen here. Now, the situation of how many circles go through 1 point in a tangent to 2 lines, there's 4 complex circles, but only 2 of them can be real. Okay, this is the issue. And so this is where we lose, this case is where we lose our count, essentially. And so then when we do this count instead, what we get is 136 real circles, which is, of course, not 184. And so that's why this degeneration argument, unfortunately, did not work out. And so when so Paul Breiting was the one who suggested this problem for the LEU. And when I knew a bit about Steiner's problem, and I kind of just assumed, you know, it's an LEU, it's a couple weeks, that this, you know, it would just be 184 and we'd all call it a day and we'd be good to go. And then at this point, when we realized it wasn't, it's like, oh man, this problem just got a lot harder, right? This might not be an LEU problem anymore. Okay, so we wanted to try something else at this point. And our second idea was, okay, maybe, oh, sorry, this cut off a bit. So maybe this kind of direct geometric argument isn't going to work, but at the end of the day, I still have this parameterized polynomial system that I can play with. And there's this family of algorithms called hill climbing algorithms, which allow you to move around in parameter space to try to find instances where you have more real solutions. And so recall, this is our parameterized polynomial system that we're talking about. So the idea here is that I would start with some instances of my A's, B's, and C's, and then I have, you know, my certain solutions, and then I want to move around in the space, the 18-dimensional space of the A, B's, and C's to hopefully find instances with more real solutions. Okay. And so the key idea here is that I can linearize my parameterized polynomial system. And so here, this Jack sub x, this is the Jacobian of my polynomial system with respect to x, and the Jack sub p is the Jacobian with respect to the parameters p. And what you see here is I've got this nice linear relationship that expresses the change in one of my solutions as a function of the change in my parameters. And so what I want to do is I want to consider some solution that is not real, and I want to minimize the one norm of the imaginary parts of this solution. And using this relationship above, I can express this as a linear function in the change of parameters. And so what I want to consider is the following optimization problem. So I want to minimize over my change in parameters, and I want to minimize, yes, the one norm of the change in the imaginary part of one of my solutions. And then my constraints here are, I think, kind of natural constraints. So the first one says that this linearization is only accurate in a neighborhood, of course, of my point, right? So I don't want to go too far, because then this linear approximation is no good. Okay. The second one says that as I move in my parameter space and I try to drive this one complex conjugate pair together, I want to make sure any existing real solutions I have stay far apart. I don't want to simultaneously drive one complex conjugate pair together and 2 real solutions together so that my number of real solutions doesn't actually change. And then the final one says I don't want any of my other solutions, I don't want them to go off to infinity. I'm kind of trying to get myself through my real discriminants and get a point with multiplicity and then push it into 2 distinct real points. And the key here is this is actually a linear, I mean, I wrote it a little vaguely because the notation does get, you know, not, you know, super pleasant, but this is a linear program, so it can be solved efficiently, and we outlined it in our paper. And also outlined, let me see, in this citation, this paper of Deep Mind. Okay. Okay, so that is step one. So I took a complex conjugate pair and I drove it together. Really good. But now what I have is I've got, essentially, instead of having two distinct solutions, a complex conjugate pair, I've got one real solution with multiplicity 2. And I'm looking for generic instances, so I want these, I don't want multiplicity, I want two distinct solutions. And so in this case, what I want to do now is I want to maximize the the distance between my two now real solutions. And again, I can use the same linear relationship above and express the change in the distance of these two solutions as a linear function in the change of parameters. And so I get a very similar optimization problem to the one we just considered, except for now my objective function has changed. Instead of minimizing the one norm of the imaginary part, I'm trying to maximize essentially the change in the distance between these two solutions, but that's still a linear function. And then I still subject it to the same constraints because, as before, I still don't want any other two real solutions to come together, nor any other solutions to go off to infinity. Okay, so this is the main idea. And well, it worked a little bit. I mean, it worked to the extent that using this, we were able to find an explicit instance of 3 conics with n real tritangent circles for each n between 0 and 136. And so here's just a little cartoon drawing of, for instance, when there's 2 real circles, here's your configuration of conics, right? So just we're able to kind of be really explicit, and then we can certify each solution, and so we can be concrete. And maybe specifically, most interesting, we can get the following conic series, a really explicit instance where this is the maximum number of real circles. But it's only 136. Oh, and I should say, we used our previous result to get to this 136. Namely, we looked in a neighborhood of 2 double lines and then ran hill climbing from there, and okay, we got to this. But okay, yeah, it's still not 184, right? So we still have not found an instance of more than 136 real tritangent circles using either the deformation argument or this hill climbing algorithm. Okay, so then this brings us to our final attempt, which is like the most vague and we don't know the most, which was, okay, essentially what I have in my parameter space, so I've got this 18-dimensional parameter space, and there's some hypersurface that goes through this space that divides the space into cells. And in each cell, my number of real solutions to this parameterized polynomial system is constant. So in other words, it divides my space of conics into cells where the number of circles, real circles tangent to all 3 conics is constant. So we thought, well, maybe if we understand this real discriminant, enough, or whatever that means, if we could get a handle on this, maybe we could say something or understand the nature of these cells a bit more. So, okay, just to be clear, when I say real discriminant here, what I mean is a hypersurface in my space of parameters where a point is on the discriminant if and only if the number of solutions to this parameterized polynomial system is not locally constant. So it's the points where my number of real solutions changes. And any configuration of conics on the discriminant we call degenerate. Okay, so what we were able to show is the following. Here is a classification of the conics that are on our discriminant, okay? So let's go through these. So I say that an arrangement of 3 real conics is degenerate if and only if one of the following happens. So the first one is that there's a real line tangent to my 3 conics, so I can maybe draw these out. So think of something like this, where I have a line like this, and then maybe here's conic 1, here's conic 2, and here's conic 3. So that's situation 1. So just a line is tangent to all 3 conics, a real line. Okay, the next one is that the 3 conics intersect in a real point. So this is something like this, maybe. And I realize I'm drawing ellipses for all of them, but that's just because I think it's easier. But these could be hyperbolas too. So this is something as follows. So this is, both of these are kind of clearly non-generic situations. The next is that one of the conics is singular, essentially. So this is, one of them is a double line. So Let me see. Just anything that looks like a double line, and then use a hyperbola.
Well, how about just a line, 2 lines? Probably what you mean by that.
That's true too. Instead of a double line, this could also have been 1 line like this. And then,
Because that forms a hypersurface in space of conics.
right, and then this could also be,
That's a single.
yeah, exactly, tangent. Okay. Let's see, what is number 4? So this is that 2 of the conics intersect tangentially. So of course 2 conics can intersect non-tangentially, but at a real point, but what I mean is I have something like this. So there's an intersection like this. And then the 5th one, let me see if I've got room. So this one, it sounds a little weird, but it just kind of came out of looking at the Jacobian dropping rank and solutions at infinity. And what this one says is, okay, essentially I can't have one of my, I can't have a situation where one of my circles is 2, let's see. Okay, maybe that's plausible enough. So I can't have a point of tangency where the normal vector for both the conic and the circle are in the same direction, and also the curvature at both is the same. So I can't have this like nicely nested situation like this. This one maybe is like the least clear why that couldn't hold, but like I said, it just kind of comes out very naturally from looking at the Jacobian dropping rank.
Yeah, I mean, you're right. That's a degenerative integration that's higher contact.
Yes, because the Hessian drops. Yes, yes. Okay, that's true.
So I mean, the number of solutions will drop. Given that configuration of conics, the number of solutions you drop that configuration because it's high, or this is a multiple solution.
Right. Yes. Yes. Yeah.
Is the discriminant hypersurface reducible?
Yeah. So generically it would be, right? If I had a generic polynomial system, it would be irreducible in the space of coefficients, but my polynomial system isn't generic. It's kind of even like parameters. Yeah.
Do you have any sense as to which of these are the more generic? Oh, the last one are most interesting.
You mean like,
Hypersurface.
is the last one a hyper?
Yeah, so each of these define a variety in the space of triples of the
Mm-hmm. But the,
such a thing exists. Okay, and the question is, are they all hypersurfaces?
oh, yeah, I'm not sure. I guess we didn't look to, but yeah, of course, because some of these might be, yeah, not.
Yeah, the last one's suggesting the last one may not be a hypersurface because it's so special.
Yes, that's possible.
I think the
You
last
think?
one is the main case. The other ones are all sort of special. Like 1 and 2 is a resultant, 4 is the tact invariant, but 5 is where the meet is.
I think so.
Do you know the degree of this hypersurface? Assuming 5 is a hypersurface, do you know the degree?
So no, we couldn't, I mean, this is part of the issue too, we couldn't actually compute these things, right? So this is some 18, you know, I'm looking for some polynomial in 18 variables. That's, my guess would be high degree, right? And we couldn't compute it. You know, that was, okay, but even if you could, I mean, I'm, you know, I'm not sure if it would help.
You might be able to parameterize that, but I mean, each like the first one's a hypersurface. You take 2 conics, just take a one-dimensional family of other conics. This can be tangent to the line. You want those tangent lines for the first 2 conics,
Yeah,
and
well,
etc.
that's degree 12, 4 plus 4 plus 4.
Yes.
That's the result.
I understand, but these are at least the first 2 are hypersurfaces. The last one, I don't know if it's hypersurface.
Yeah, we didn't look, I mean, that would probably be the natural, that would be the first thing probably to look at. Okay, like what of these components actually matter is another way of saying this. Yeah, okay, and to be honest, I think at this point there was not a lot of direction of like, okay, even like how does this help? Because, okay, even if you knew the dimension, I think that's step 1, but we care about the cells, we care, right? And so you know, what of these components are on the boundaries of different cells to, I mean, this is, yeah, it just wasn't clear. It wasn't clear how this could help is really the main story. And to Baron's point, we couldn't compute it But okay, even if we could, I'm not sure that that would help I'm not sure how having an explicit polynomial in these 18 variables, which I'm saying this is my discriminant, I'm not sure how that would help me still say that there's at most 136 real solutions, because this polynomial is probably quite nasty to deal with, right? So, okay. But let me just sum up and say, yeah, okay, we did it, and that's very nice. But it's still not at all clear how this helps us answer this main open question. So this is really the main point of this shorter talk, but longer open problem presentation, is to say, does there exist a configuration of 3 real conics with 184 tritangent circles? Or also, can you prove that no such configuration exists? Can you prove that 136 is the maximum, or can you prove that there just has to be less than 182? I think I think that would still be just as interesting in some sense. And part of the issue is when we were looking, through literature, of course, of these enumerative problems, is it really seemed like most of those problems, the maximum number of real solutions was the complex bound. So there was an instance of whatever objects you were considering where, the maximum number of, or the number of, whatever other object you were considering that's tangent to, passes through, whatever, it is all real, right? So we didn't really have a lot of other things to work with here. And so with that, I said I would end 10 minutes early, and so that you all can, spend the next 10 minutes solving this, and I'll just end with, happy birthday, Frank. Yes, I'm sorry we couldn't solve this for your birthday, but, we did the best we could, yes.
Questions?
So often when the real count is below the complex count, then the Galois group is smaller than expected. What about the Galois group?
I think it's a full symmetric group. If I remember right, almost the full symmetric group. Yeah. But is there a result that says that if it's okay? Okay.
So what? Okay, it's almost a tautology. If you have some structure, the possible number of real solutions, like gaps or other things, then this could come about because the Galois group is smaller than expected. So if you have some incurvative structure, but it's not a theorem.
Okay.
If you understand it, it's something to do with the possible field extension you have.
Okay. Okay. Oh, and Gabriel. Oh, Gabriel. Hey, Gabriel. He confirms. Okay, it is the full symmetric group. Great. Okay, perfect. Yeah.
So I just wanted to make a comment on a lead in case anybody is interested in solving this today for Frank's birthday.
Yes.
If you only degenerate 2 of the conics to double lines, but you keep the third conic just a conic, then you decompose into like tangent to a conic, tangent to a line, or tangent to a point, those subproblems. And individually, those problems do have enough real solutions where when you do the count, you get above 134. But I don't know if all those subproblems can be totally real.
I see. Okay. Yeah.
So
Right.
even individually, I don't know if they can all be totally real, but we could find instances where you got enough real solutions to get higher than 134, just not to 180 or 136, but not to the 180.
Okay.
Yeah.
Yeah. Okay. That's probably the next natural thing to try. In some sense, is there a different degeneration that we could? Yeah.
It's a little less special.
I mean, there's a good chance you're not going to be 184. So it's known that if you have lines and real points in convex position, as both Lindberg and Chris have shown this, then you'll always find the correct number of conics that are tangent to the lines or passive to the points. And that's actually how one way of proving this pentagon. I'm sorry, maybe I did this. Yeah, it's known that if everything's a real and convex position, then you'll find the expected number of conics tangent to the lines and through the points. But because the 2 circular points at infinity are not real, and I don't know what convexity means there, that's an obstruction to finding them.
Yes.
That's probably why it's one reason you find out why, but it suggests why you can't do that.
Right.
But there are other examples. I one time wrote a silly little paper where we looked at 4 triangles in space and looked at lines that simultaneously meet one edge for each of the triangles. And you can show that not all can be real.
Okay.
And which is a different sort of a question. But
Right.
Two things. The first thing is this, am I coming through the speaker? Is this working? Okay, good. The first thing is you talked about starting with double lines and then seeing that you couldn't get all of the circles to be real when you had double lines because of this one case. And so my first question would be, do you know if the kinds of techniques involved in hill climbing would make it possible to take a more generic configuration and then to try to move it into this special configuration to see if you could do that without reducing the number of real solutions?
You mean don't initialize my hill climbing in a neighborhood of double lines. Initialize it someplace else.
And then try to go to double lines.
And then try to go to double lines.
And if you could do that in a hill climbing way, then that would mean that you'd started with fewer than 136.
So the 136 is very rare, let me say. I don't think we found that, Gabriel, maybe you can say yes or no. I don't know if we found that naturally by like randomly initializing. I think we had to initialize in a neighborhood of this special configuration to get there. But if I do just randomly initialize, say, the hill climbing will take you from, I don't know, maybe an instance where you have 80 real solutions to 110 real solutions, something like this. Like it's effective to a point, right? It can bump you up by kind of a non-trivial margin, but I think if I remember right, it wouldn't get you just all the way to the 136. Or maybe we would have had to initialize more.
I'm not trying to get to the 136. I'm wondering if you could try to make your system less generic, make it more special by trying to deform 2 where you have only double lines.
Oh, you mean like guide the hill climbing algorithm
and,
to
guide
the
it
double
in
lines?
such a way that you know you're not losing solutions. And then you would have already known from your previous analysis that your total at the end would be at most 136. So if something like that were possible, then it could maybe give you a bound. The second question that I had was, could you show us the definitions of the cases you put on the board one more time?
Yeah.
I just wanted to read 5 a little more carefully. Thank you.
Yes. Oops. Yes, and this is actually in a paper that's published called Real Circles Tangent to 3, the name of the talk, Real Circles Tangent to 3 conics, yes. This is.
These are circles and quadrics that have one of the conic tangent then to the special points has a higher order of time factor. So that's probably how we show this. They all seem like except for maybe.
So I have a comment that might help. Frank mentioned that the circle points at infinity might have something to do with it.
Yes.
If you switch to an isotropic coordinates and work in a 2 homogeneous space, then the circle points at infinity aren't there anymore. So when you look at it that way, if you don't know what isotropic is, it's basically instead of x squared plus y squared equals r squared, you do x times x conjugate. And then your notion of real is that the conjugate really is the conjugate.
Right. We didn't try that, but that would be nice to look at as well.
The non-standard real structure.
Right. That's great. Yes. Okay. That's good. We did start in a.
Can you also, hi. Can you please see the result on 136 this thing, conics, because what was this thing about at most 136 solutions?
I'm sorry, I couldn't hear you.
There was a theorem about at most 136 solutions, right?
Real solutions, yes.
So why is it, so if it is already mentioned at most, why are we trying to find more 184?
Oh, we just wanted an explicit instance. I mean,
Can you show that slide again?
Sure, maybe I'm not understanding, but there's kind of two. it's like constructive, right? It's kind of nice to be constructive in a sense. So okay, this argument, we kind of use a really analogous thing to what's done in Steiner's problem. Say, okay, there exists 136, but sometimes it's nice to just have the object, right? And so we just wanted an action, we're just interested in getting the actual.
So I thought there was a previous slide where it was mentioned as a theorem where there were at most 136 solution, or did I misunderstand? Oh.
Yes, just in a neighborhood, right, so that's the issue, right? If we could if we would have shown that in any neighborhood of the discriminant, there's, okay, we would have won, but we could only show in a neighborhood of the special configuration. And the reason why, we would consider that in the first place is because of this classical result of Steiner's.
Okay, thank you.
But yes, so it would be, if you could show in any neighborhood, of, maybe this was, if you could show in any neighborhood of one of these cases, you get at most 136, okay, then we win.
Other questions? Well, then we thank Julia again.
Thanks.